Chapter 4.3 is where we're going to take stoichiometry up to a more AP level. So Chapter 4.2 is a reminder of what stoic is. It was honors level stoichiometry. You're given a value of one substance and you have to convert it to the value of another. Chapter 4.3 puts it in a more real life scenario, which is what if you have multiple grams of multiple products? How would you figure out which one is going to determine the amount of product you can make? What I mean by that, if we go back to our kitchen scenario here, say we go back to the 6 cups of cheese that we had in the last video. What we're assuming with the 6 cups of cheese and converting that into 3 pizzas is that we have plenty of crust and sauce. So these are what we would call the excess reagents, meaning that if the cheese is what is determining how much pizza we can make, then that means we must have had plenty of sauce and plenty of crust. In a real life lab scenario, you don't just have an infinite amount of all of your reactants. Okay, you'll have a certain amount of one reactant, a certain amount of another, and when those two things are colliding with each other, one of them is going to run out first, and that's what we call the limiting reagent. So in this case, the cheese worked as a limiting factor because it limited how many pizzas you could make. If we're looking at an example of that, let's say now you have a real life kitchen scenario where you have a certain amount of crust, a certain amount of cheese, and a certain amount of sauce. Okay, well, what you need to figure out is based on those 3 reactants individually, which one of them is going to limit how much pizza you can make. So the bad news is you have to do stoichiometry for all 3 of them to figure out which one makes the least amount of pizza. So if we have 4 crusts in the kitchen and we're assuming we have tons of cheese and sauce, that was capable of making 4 pizzas. If we have 10 cups of cheese, that is capable of making 5 pizzas. But the sauce is we only have enough sauce to make 3 pizzas. So the sauce is what we call the limiting reagent. Okay, it is what's going to determine how much pizza we can actually make, because once we run out of sauce, in theory, we cannot make any more. So the cheese and the crust are what we call the excess reagents, and the sauce has now become our limiting reagent. If we look at a actual chemistry example of this, okay, we're going to talk about molecules here, which is the same thing as it already being in moles. So we're going to start small and work our way towards longer problems. If we've got methane, a limited amount of methane and a limited amount of oxygen, we can try to figure out how much carbon dioxide could be made, but we have to do stoic for both of those in order to figure it out. So I'm going to begin by setting up 2 separate stoichiometry problems. Again, molecules and moles, those can both be compared to you can use a ratio, a stoichiometry ratio for that, so we don't need to do any converting. Okay, we can just jump right into the stoichiometry. So for every 1 methane, we can make 1 carbon dioxide, which means this could make 5 molecules of carbon dioxide. All right, so the methane's capable of making 5. If we look at the oxygen, for every 2 oxygens, we can make 1 carbon dioxide. So that means the oxygen is capable of making 4 molecules of CO2. So what we're looking at here is we've got both of these happening at the same time. The methane, we have enough methane to make 5 carbon dioxides, but we only have enough oxygen to make 4. So that means the oxygen is our limiting reagent, and the real value that we would predict of what we could make has to be 4 because we are not able to make 5. There's not enough oxygen to go there. Most of the questions that you would be solving are going to look just like this. So you're going to have a reaction that's balanced. It's going to have at least 2 reactants trying to make a product. And in this case, this is the one that we used in lab. Okay, we've got magnesium reacting with oxygen trying to make magnesium oxide. So this question is suggesting that we have a limited amount of magnesium and we have a limited amount of oxygen. Which one of them is going to run out first? Because that would be our limiting reagent, and that's going to determine our actual theoretical yield of magnesium oxide. So I'm going to begin by just looking at magnesium. So we're going to have to do a whole stoic problem of magnesium and then do a whole stoic problem of oxygen and then compare them to each other. So the first thing we need to do is convert to moles. So we have this many moles of magnesium, and then we do the actual stoichiometry where we convert magnesium to magnesium oxide. And we can stop here for now because we're not solving for how many grams of magnesium oxide we can make yet. First, we're just trying to figure out how many, like which one of them can make the most amount of magnesium oxide and which one can make the least. So now I'm going to just forget about magnesium and look at oxygen. If I take my 33.8 grams of oxygen, figure out moles, and then do the stoichiometry step, okay, that tells me that the oxygen is capable of making 2.12 moles of magnesium oxide. So now I have to compare the two. We just figured out that with the available amount of magnesium, we can make 1.75 moles of magnesium oxide. And with the available amount of oxygen, we could make 2.12 moles of magnesium oxide. So what that means is we're limited by our amount of magnesium. Okay, the maximum value that we can create of magnesium oxide is going to be whatever the lowest number is. So 1.75 is going to be our maximum value because we're going to run out of magnesium. So the excess reagent is oxygen, and the limiting reagent is the magnesium. The third step for this is to figure out theoretical yield. So we're going to take our limited amount of magnesium oxide, multiply by molar mass, and that gives us a theoretical value of 70.5 grams magnesium oxide. Okay, so one more time, just running through this. Okay, we have two values for both of the reactants. We had to set up two Stoich problems, starting with both of those. One of them told us that we could make 1.75 moles of magnesium oxide. The other one said we could make more than 2 moles. Okay, the limiting value is the lowest number, and that's the one that you have to pick, because what it's saying is once you have made that amount, that means that that reagent has run out. So you have extra of the other one. And in this case, we had extra oxygen and we were limited by magnesium. And our found value was 70.5 grams of magnesium oxide. Okay, there is one additional step that you did in your lab. Okay, we just said theoretical yield is 70.5, and much like in your lab, this reaction is suggesting that we did not get 100% of what we expected. So if the reaction only provided 55.9 grams, okay, we're going to take that value, divide by theoretical, multiply by 100, and that gives you your percent yield, which in this case is 79.3%, so better than the lab went. All right, one last example. The longest that these questions can get are that they give you, or they ask you for what's the limiting reagent, what's the theoretical yield, and what's the percent yield all at the same time. So deciphering through this question, okay, here's the iron oxide. So you have 167 grams of this. Okay, we have 85.8 grams of carbon monoxide, and it says the reaction produces 72.3 grams of iron. So this is going to be the product we compare both of the reactants to. And we're going to see, you know, is it 72.3, or are we going to predict that it actually should have made more than that and compare it to the 72.3? So I'm going to begin by starting with just the first number I see, which if I go back is the 167 grams of iron oxide, and we know that we're comparing both of these to iron. So my first step is convert iron oxide to moles, then do a stoichiometry step to see how much iron that much iron oxide can make. So the iron oxide is predicted to make 2.10 moles of iron. Second step, okay, is to take the next number, which is the mass of the other reactant. Okay, we're going to take 85.8 grams of carbon monoxide, turn it into moles, then do stoichiometry to see how much iron it would make. So the amount of carbon monoxide we have could make 2.0 moles of iron, while the amount of iron oxide that we have up here could make 2.1. So what that means is the maximum of value of iron that we can actually produce is 2.04. Okay, carbon monoxide is our limiting reagent, and iron oxide is what we would call the excess reagent. So our reaction is limited by the amount of carbon monoxide, and it's going to stop producing iron at 2.04 moles. to figure out what the theoretical yield is. This is the theoretical yield in moles, but that's not a very usable number. So we have to do a last step where we take moles and convert it into mass. So we use the mass on the periodic table, and that means our theoretical yield is 113.9. If we're keeping with sig figs, I would say that's 114. And the very, very last step is to compare what we theoretically can produce all the way back to what it says we actually produced. So in this case, it says you really only collected 72.3 grams of iron. So to get percent yield, which is the last step right here, okay, we do 72.3 grams divided by 114 grams times 100, and we get 63.4%. Okay, yes, I realize that this is an incredibly long problem, and the bad news is that there is no short way to do it. But the good news is that all of the questions are essentially the same, just like it's just stoichiometry over and over and over again. The tough part is keeping up with your units. Okay, you have to remember what you're working on, be methodical, and learn the process, okay, beginning with grams, going to moles, doing stoichiometry, comparing them to each other, etc. Try the homework out, bring your questions with you on Monday.